So I'll go to the second half of the presentation then. All right, so like the other one, this is based on a set of presentations by other people, and I've included the links here. The third of these, which I think is a very exciting piece of work, you know, I will mention it, but I really won't have any time to cover that in detail. But I'll cover a good part of the other presentations. So the you know, the matrix math assist functionality that I'll talk about is included in Power10, and I'll start with a brief overview of the Power10 chip and systems. So this is actually I think we started shipping the first Power10 systems in I think it was September last year. They are we have large cores in these processors, you know, eight-way multi-threaded cores, and they tend to deliver about 2 times the performance of a maybe more typical industry standard core, right? So this 16-core processor is something you can compare to maybe a 32-core industry standard one. You know, very substantial amounts of SMP and memory bandwidth, you know, up to 1 terabyte per second. And I'll go into that a little bit more. And actually, our systems, we use these cores in 2 configurations. Either, you know, one of these cores in a socket, or you know, other modules where we put that's in our lower end and mid-range systems, where we put two of these chips in one socket. Like I mentioned, you know, it's an impressive chip, not only from a compute perspective, but also from a bandwidth perspective. You know, terabyte per second of bandwidth to memory, as well as to the fabric between the chips, right? The SMP fabric, and it can be used, you know, not only to build an SMP, could be used to build a processor with or a system with a tremendous amount of addressable memory, you know, up into the petabytes actually, as well as for accelerator attach. So I'll talk a little bit about memory here. So the way we achieve this very high memory bandwidth, which, you know, when you're actually building HPC type applications, right? You depend not only on having very good compute density, but, you know, to have a good breadth of applications that deliver high performance, you need to balance that compute with a lot of memory bandwidth. And in the case of the power systems, and we've been doing this for a while, the way we achieve that very high bandwidth is by actually having you know, high-speed serial links between the processor and a buffer that expands that interface into you know, the wires that go to the DRAM chip. So by using these very high bandwidth signaling lanes, we can support both very high memory capacity, which is required in our database systems, you know, when we use this for things like SAP HANA, and our current systems support up to 64 terabytes of DRAM, right? This is not you know, flash or disk or something like that. This is actually DRAM memory, 64 terabytes, you know, and very, very high bandwidth. And you know, that is possible by you know, here's actually the most recent one, right? So a standard DIMM this is actually also one of these DIMMs based on the serialized interface, and this chip here, bridges between that serialized interface and the interface to the DRAM, the conventional DRAM channels. This DIMM, in terms of its capacity, looks more like a standard DIMM, but in our 4U and 5U systems, we can build much larger DIMMs that have a lot more memory capacity, and support memory chips on both sides. And I think it goes up to like 80 chips per thing here. And this, for those of you who are familiar with the CXL, follow on to PCIe and the CXL attached memory, they're following, I think, this approach with their form factors for memory look somewhat similar to this. I mentioned both single socket and dual socket modules, and for the dual socket modules we go up to 4 socket systems, and for the single socket modules we go up to 16 socket systems. And this is a slide on this what we call memory inception. Basically, it's a form of cluster shared memory where you can create load store addressable address spaces that cross multiple computers with each their own operating systems and hypervisors, and it builds on some of the concepts from the OpenCAPI work that we did before, and the basic notion is that we we can also, when we have an OpenCAPI interface, we have a virtual address. Actually, in the case of Power, it's an effective address, but you can think of it as a virtual address that we use to allow accelerators access to the memory inside a host. But when we do, when we take that, and then in the host it gets mapped to, for example, an OpenCAPI memory interface where it comes out as a physical address. So on these OpenCAPI interfaces, we have both, physical addresses as well as virtual addresses. And then if we introduce a mapping back from physical to virtual, then we can have a memory port that is normally used to attach to a DIMM. We can, turn that address into a virtual address that the next server can understand, and this way, kind of do what Bill Starkey calls routing through the page table and create large systems. And because our SMPs are very, we've set the fabric up to have low latency for SMP type structures. This is a low latency way, to create a large memory address space. So, we'll go into the compute aspect next, but in terms of memory bandwidth, we have a very substantial improvement on Power10 as well, right? So a good balance between the memory and compute side. Okay, so now let's start talking a bit about the core and this matrix multiply assist. So in general, going from Power 9 to Power 10, we improve performance by performance efficiency by a factor of 2.6, and we added quite a bit of AI and enhanced floating point capability with the matrix multiply assist. So we also grew our vector instruction capability by a factor of 2 relative to by a factor of 2 per core relative to what we had on Power 9, as well as grew the number of cores from Power9. I'm going to go a little fast over the some of the microarchitecture things. What you see here is a list of all the enhancements from Power9 to Power10, right? So when you see a 2x, 4x kind of a number here, that relates to the ratio of that particular attribute relative to Power9. So one example here is this the SIMD capability. We have and what's shown here is actually half of an SMT8 core. So we have 4 SIMD lanes within that half. And I'm going to go into the matrix, the MMA functionality in a little bit. Grew things like queue sizes, cache sizes, things like that. Bandwidth is also enhanced, right? Important to when you grow the compute, right? Doubling the SIMD capability, for example, as well as introducing the MMA, you have to have the bandwidth to feed it. Otherwise, the only thing you can do is show maybe a compelling impact number or something like that, but not something great on actual applications. And then other things like in every generation, of course, you try to improve your branch prediction and instruction fetch architecture as well. And then we actually added a number of architectural innovations, introducing new instructions. I think one thing that is not mentioned here, but is quite relevant, is that we did we introduced instructions that use more than 32 bits, so-called prefix instructions. That are especially important for things like longer distance branches, where we needed a sequence of instructions previously, but it's also helped us open up the instruction space for other purposes. And the net of all this was that we've grown per core performance by 30%, single thread by 20%. Oops, sorry, and overall, we improved our power per core by a factor of 2. And if you combine that with this 30% performance per core, you come up with a 2.6x improvement at the processor level in terms of performance per watt, which is a very substantial improvement. So now I'm going to talk in a bit more detail about this matrix multiply assist functionality. I mentioned the enhanced bandwidth in the processor, right? Both internally within the processor in terms of its data paths to the caches and so on, and as well as the bandwidth out to the off-chip memory. Here in this table on the right, what you can see is the peak flops that are achieved, for the different precision levels: double precision floating point, single, half. bfloat 16, we added bfloat 16 support in the architecture, and actually go down all the way to int4 data types. We doubled the number of SIMD engines, as I mentioned, and then introduced this matrix math function that I'm going to talk about next. Actually, let me skip this slide and talk about matrix math. So all of you are, I'm sure, familiar with the normal type RISC instructions, right? Where I might have a you know, two sources and a destination. The destination here is shown in green, and the operation may be something as, you know, 8 times x plus y, right? A floating point multiply add, giving you two flops per cycle. With SIMD, you do something very similar, except that now we use vector registers, which in the Power architecture, typically 128-bit wide. So if these were single precision floating point numbers, then you could have 4 of them in a SIMD register, and instead doing an you know, a equals ax plus y operation on one of these elements, you do it on 4 elements at a time. And if this, you know, so that in the case of single precision flops, it would give you 8 floating point operations per cycle. Now with matrix, it actually works a little bit different, because in order to, you know, go the next dimension up, what you see here is that the stuff in green, you know, is not the same number of elements as the input registers, right? So what we did is in the architecture introduced so-called accumulator registers, which are 512 bits wide instead of the 128-bit wide vector registers. And the primitive that is implemented here is basically an outer product type rank 1 update, right? Where you element-wise, you know, take the previous value of that particular element in your what you can, you know, matrix register, and update it with you know, with ax plus y for you know, for the input vectors, right? Oops. So this now gives you, again, if these are single precision floating point numbers, you know, instead of the 8 flops per cycle, right? Multiply, add, remember. It gives you 4 times that, you know, 32 flops per cycle, using still 2 vector input registers, but now accumulating into this matrix register rather than another vector register. Now this all works out, you know, simply for 32-bit float. If you have you know, other data types, then you know, it works out a little bit differently. So for example, if you do things with 16 bits, you know, obviously your input registers would only be, which are 128-bit wide, would only be half used, right? If I had 4 elements in there, that would be 64 bits. So what you do is you actually consider that to be 2 ranks, you know, of a matrix, and you do a rank 2 update into your matrix register. In the case of you know, you know, and so on for other data types. In the case of double precision float, you can actually only do, you know, half of a full rank update, because you know, you can only hold 2 double precision floating point elements in a 128-bit register. So in that case, we need to engage two of our matrix units to do a full rank update, and you'll see a detailed example of how that works. So, you know, as you can imagine, with all these different data types and variations of these instructions, it actually adds quite a few instructions to support all of these different data types, as well as you know, multiply, add, and multiply, subtract, and negating, you know, the one or the other element. The way it's supported is through built-ins, so that you know, a lot of the management of the registers and other things, you know, can be left to the compiler, right? So you see that these operations here, typical operations here take that accumulator register, as well as two of the vector registers as inputs. So for DGEMM, as I mentioned, right, you know, if you're, maybe the easiest way to think about it here is if you're going to do an 8x8 update in software, you know, each of the operations themselves is going to be, you know, a 2x4 across these different registers, and if you do the math, you'll see that you need, you know, that you need 8 of them to you know, to create that 8x8. But the principle is really the same, and this is the you know, what it looks like in code with the built-ins, and this is the you know, what comes out of the assembler. And indeed, you know, when we look at the performance going from Power 9 to Power 10, if we just use the SIMD capability, we double our performance. Actually, when we use the matrix math capability, we more than double the performance, and the reason is that we have an ability to still use some of the SIMD capability in parallel with the matrix math capability. So that's why it's a factor that's a little bit bigger than a factor of 2, going from SIMD only to SIMD plus MMA. So it's, you know, it's a very powerful processor, and you know, as you would expect, this leads to you know, very good numbers on things like DGEMM and LINPACK and so on, because a lot of attention was paid to power efficiency. We actually managed to do this without having to significantly reduce the frequency of the processor. So, you know, you can use these matrix math capabilities without severely throttling back on frequency, which is nice. And you know, for AI and machine learning, as you would expect, because it's typically floating point matrix math dominated, we actually see those speed ups that we expect from the peak floating point rates in you know, in actual evaluations of large models. Now, the last thing I wanted to mention here is you know, so I've emphasized that the power architecture not only, this implementation not only gives you high floating point density, but it also supports it with very good bandwidth, you know, throughout the processor and memory subsystem. And I think one example where you can see this is on what we can achieve on sparse-matrix math. So, you know, I've introduced a link to this work. So there is you know, there's a bit of innovation here in the formats as well. You know, a new way of storing sparse matrices that actually allows you to use both the matrix unit and the vector units effectively when you execute on this. And you that innovation with the capability of the power architecture, right, to support both that matrix and vector side, gives you a factor of 2 improvement. And the net result of all of this is that we've achieved over a teraflop of sparse-matrix performance on a Power10 processor, and this was actually on the single socket processor, which is a there are a lot of architectures that achieve very impressive numbers on dense floating point math, but personally I'm a lot more impressed by that result that was achieved on sparse matrix math. So I don't have time to go through this in any detail, but I included a link to a talk on YouTube, and you can find the paper online that describes it. I think this was a very nice, nice piece of work, and I think that's really all I wanted to cover today, and I'll leave last couple of minutes here in case there are questions.
Yeah, Peter, there is a question in the Q&A window.
Okay. Yeah, so we, of course, so I talked about inferencing, right? When I showed the like BERT large and ResNet 50 type models, but that's on large models, right? Inferencing on large models also becomes floating point dominated. There's nothing that stops you from doing training on a power processor as well. But if you're doing training, you tend to be, when you're doing inferencing, it's usually in the context of some kind of a business application that puts a variety of general purpose demands on your architecture, right? When you're doing training, on the other hand, you're just very floating point dominated, and of course the power processors and systems are focused on these business applications, so they're not designed to optimize the training aspect alone. Oh yeah, that's a good question. Yes, we have PyTorch, TensorFlow, and I'm forgetting one. ONNX. Those are the 3 frameworks where we've upstreamed open source support, right, for MMA. It's through a library called OpenCE, and yes, indeed, those frameworks support the Power10 MMA functionality. Good question. Thank you for asking. That's I should have mentioned that. Right. So underneath those frameworks are the libraries like OpenBLAS and Eigen and MLAS, I think, for ONNX. Yeah. Yeah. Okay.
Any other questions, team? So, okay. Thank you, Peter.